All right, today we're jumping into a really clever piece of offensive security tooling called BlackSerpentine. It's all about solving a classic problem. How do you get the raw, low-level power of C into the nimble, flexible world of Python and do it all without ever writing a file to disk? It's a fascinating approach to building stealthy, fileless implants. Okay, let's get into it.
So this is the central question, right? How do you take the raw, system-level power of a language like C, but wrap it in the agility and speed of Python, all while operating completely in memory so you don't leave a trail for defenders to find? For stealth operations, this is kind of the holy grail.
So to really appreciate why a tool like BlackSerpentine even exists, we first have to understand this fundamental challenge that red teamers and malware developers face all the time. It's this constant tug-of-war between power and agility. And it really boils down to this choice of weapon. On one side, you've got Python. It's fantastic for rapid development, for networking, for just being incredibly flexible. But it's a high-level language. It's kind of sandboxed away from the real nitty-gritty of the operating system. Then, on the other side, you've got C or C++. This is the language of pure power. You can talk directly to memory. You can mess with system structures. The sky's the limit. But it's also way more complex. It's rigid, and it's just slower to build with. So the dilemma is, you want Python speed, but C's power.
And that dilemma, that desire to have the best of both worlds, is exactly where BlackSerpentine comes into play. It's specifically designed to be that bridge, connecting Python's ease of use with C's raw, unadulterated power.
So what is it, exactly? Well, at its heart, BlackSerpentine is a beacon. It's a small, lightweight implant written in Python. Its whole job is to call home to a command and control server, ask for orders, and then carry them out. But here's its secret weapon, the thing that makes it so cool. It can take compiled C code, what's often called a beacon object file or a BOF, and run it directly inside its own memory space. No files are ever dropped on disk. No separate C program is ever launched. It's just one seamless in-memory operation.
Okay, so now we know what it is. Let's start peeling back the layers. We're going to take a look at the anatomy of the beacon itself, how it operates day to day, and how it keeps its communications under wraps.
You know, the operational loop, its heartbeat, is actually really simple and effective, and that's key for stealth. First, it checks in with the C2 server. If a task is waiting, it grabs it. Now, that task could be a simple shell command, or it could be the main event, a command to run a powerful C-based BOF. It executes the task, gathers up the results, sends them back home to the C2. And then, and this is crucial, it goes to sleep. That sleep cycle is what helps it stay off the radar. The communication itself is also built for stealth. It's not just sending data in the clear. All the traffic back and forth is encrypted with AES 256. And check out the configuration here. The C2 address is what it is, but look at the path. It's malleable. This means an operator can change this malleable path to look like totally normal, legitimate web traffic. That makes it so much harder for network defenders to spot the beacon's check-ins among all the other noise. Okay, we've got the basics down. Now it's time for the main event. This is the real engineering magic that allows a simple Python script to pull off this incredible in-memory trick of running raw C code. This is the core technical hurdle they had to overcome. You've got this blob of compiled C code, an ELF file. You can't just tell Python, hey, go run this. It doesn't work that way. You have to manually do the job that an operating system's loader would normally do, but you have to do it all from inside your Python script. You've got to parse the file format, place it in memory just right, link it up with any functions it needs, and then finally flip the switch to make it executable. So the creator of BlackSerpentine built this amazing pure Python ELF loader that pulls this off in 4 distinct phases. First, it pre-resolves symbols. That's just a fancy way of saying it finds the memory addresses for any external functions the C code might need, like MCPY or something from the standard library. Second, it maps the different sections of the C code into memory. Third, it applies relocations. This is the critical step where it patches the C code, telling it where everything now lives in memory. And finally, the 4th step, it applies the correct execute permissions to that memory, which basically gives the CPU the green light to run it. Now, to really get what's happening in phases 2 and 3, you have to know that an ELF file isn't just one giant block of code. It's more like a kit, broken up into different sections. The text section, that's the actual machine code, the instructions. The data and BSS sections hold all the variables.
But crucially, you've got sections like real.txt. You can think of these as a set of instructions for the loader. They literally tell it, hey, go to this spot in the text section and patch in the final memory address of this function. The Python loader reads all of this and just pieces the puzzle together in memory. It's brilliant.
And that final phase, phase 4, has this really smart security feature built right in. The loader is super careful. First, it sets aside memory as read and write, which lets it copy all the C code and patch it up. But, and this is the key part, after it's done writing, it uses a system call to change those permissions to read and execute only. This enforces a super important security principle called write XOR execute. It just means a piece of memory can either be writable or executable, but never both at the same time. This makes it way, way harder for someone else to hijack the process.
So, the C code is loaded, it's patched, the memory is ready to go, it's time to run. But this introduces another big problem. Running raw, low-level C code can be, a little unstable. What happens if there's a bug and it crashes?
This is a critical question. Because if that C code you just so carefully loaded has a bug, a segmentation fault or something, it's not just going to stop itself. Nope. It's going to take the entire Python beacon process down with it. Suddenly your mission is over, the connection is dropped, and you've just made a ton of noise for defenders to come and investigate.
And the solution they came up with is just so elegant. Look at the two scenarios. Without a safety net, a crash is a total disaster. The whole beacon just dies. But BlackSerpentine uses a safety net. It makes the risky C code run on a totally separate temporary memory stack. So now, if the C code crashes, it only messes up its own little temporary sandbox. The main Python beacon, safe on its original stack, is completely fine. It just keeps on running.
So what is this safety net? It's this tiny little companion library written in C called libbootloader.so. The best way to think about it is like a stunt coordinator on a movie set. The Python beacon is your big-name movie star. You absolutely do not want it getting hurt. So when it's time to do a dangerous stunt, like running this unknown C code, it calls in the stunt coordinator. This little library sets up a safe environment, lets the C code do its risky thing, and then cleans everything up, making sure the star is never, ever in harm's way. And this is the actual magic right here. Now, don't worry, you don't need to be an assembly expert to get what's happening. Just look at the logic. The very first line saves the current stack pointer, that's the beacon safe main stack, and tucks it away. The next line switches to a brand new temporary stack. Then it calls the C code. And once that code is finished, the last line brings back the original safe stack pointer as if nothing ever happened. It's this beautiful low-level dance that perfectly isolates the whole dangerous operation. Okay, so we've been deep in the technical weeds, and it's some seriously brilliant stuff. But let's zoom out for a second. What does all this clever engineering actually mean for cybersecurity as a whole? Why does an architecture like this really matter? Well, for attackers and red teamers, this is a huge step forward. It gives them the best of both worlds, Python's rapid development cycle with C's absolute power, all wrapped up in a stable, fileless package. It enables a new class of sophisticated implants. But for defenders, this is a serious wake-up call. The game is changing. You can't just rely on scanning the hard drive for bad files anymore. The real fight is moving into process memory. You need tools and you need skills that can look inside a running process and spot weird behaviors and anomalies. And that brings us to the final thought here. Tools like BlackSerpentine aren't just cool projects. They really do represent the cutting edge of offensive tooling. And as attackers keep finding these clever ways to blend high-level and low-level languages to fly under the radar, it forces us to ask a really critical question. How do our defenses, our tools, and our strategies have to evolve to catch a threat that doesn't exist on disk, but lives entirely as a ghost in the machine?